All right, we will now proceed with our second speaker in a popular section of the meeting. It's Professor Gunther Hasinger, who is also director of the Institute for Astronomy at the University of Hawaii. Gunther is an expert in X-ray astronomy. He played a very prominent role in a number of important space missions. He also won a bunch of prizes, which I will not read, too many of them. And he's also an accomplished popularizer of science. So without much further ado, I'll yield to Gunther.
Thank you very much, George, and thank you very much for inviting me. It's a great pleasure and honor to give this public lecture. Also, I have to admit that Lord Rees is a hard act to follow. But on the other hand, the way he set up his lecture is perfectly leading into the way I have set up my lecture. So he has introduced all of the concepts that I can then skip over or maybe just rehash. And what I would like to do is, mic is on? Yeah, I can put it a little bit closer. Sorry. Okay. What I would like to do is start from the beginning and with the question, what is empty space, actually, because empty space is playing a very important role in all of these concepts. And I'm actually stealing several of my view graphs from Stephen Hawking. What is nothingness? And nothingness turns out to be much more complicated than we ever thought about it. If you are pumping out everything from this room, you remove the people, you remove all the air, you cool it down to 0 degree so that there is no heat waves in there, you will still find something in there. And this something is actually quantum fluctuations. And as the way Stephen Hawking has pictured them, these quantum fluctuations are small virtual particles which borrow their energy from nothingness, and then they live together for a short while, and then they decay and give their energy back to nothingness. Now, this is not just a figment of imagination. This is really required by quantum mechanics in order to explain Heisenberg's uncertainty principle. And the problem, I think one of the biggest problems in our understanding of physics is that the quantum mechanical energy density of nothingness is about 120 orders of magnitude larger than what we actually find in the cosmological constant. So it's not so much the question, why is the universe filled with a cosmological constant? The question is, why is it so small? And this 120 orders of magnitude is one of the biggest numbers in current physics. I will come to other large numbers, and we will come to the fact that the black holes, as Maarten Schmidt has shown in his last but one view graphs, and other structures can actually live for an extremely long time. And that is the kind of bridge that I would like to take. So these virtual particles, in principle, you can regard them as something like a bubbling pot, like a boiling water pot, which is producing bubbles. And these bubbles, this is how to visualize more or less chaotic inflation. Each one of these bubbles you could, in principle, regard as a little universe in its own out of these multiverses. And actually, when you calculate the Einstein's equation, if you have no matter in a universe, but you have a non-zero energy density in space, then what you automatically get is exponential inflation. And so inflation as such is not really a big mystery. I think the big mystery is, why did inflation stop, and why did it basically produce our universe? Why didn't it inflate forever? And so what Maarten Schmidt already has shown, what we are coming to in a second, is that these fluctuations in empty space before inflation are actually the ones that we are still seeing in the cosmos today, and that we are all basically made out of these fluctuations originally. Now, chapter 1, what are black holes and how do they form? So Maarten has already said that black holes are some of the simplest cosmic forms, cosmic celestial bodies. They can be described by a very small set of numbers, by a mass, a spin, possibly a charge. And then only when you come into more complicated incarnations of physics, like the 11-dimensional string theory, then black holes might actually indeed get hair instead of having no hair, like in the classical theory. Black holes in this way, you will never be able to discover them because they are just dark. And the only way to discover a single black hole in space would actually indeed be if it is shadowing, if it is curving the space around itself, so you would get funny structures on the sky. The only reason why we can actually discover black holes is because they are changing their environment so much that the matter is basically then reacting to this change in environment. And as we will see, when a proton is falling into the black hole, it is kind of radiating its last cry of help in electromagnetic radiation, and that is what we can see. So we never see inside the hole, but we can actually infer something about the existence of the black hole from the space around it. Now, as I said, it's relatively simple numbers are guiding a black hole. Actually, we have already heard today from Donald Lyndon Bell that the very first person thinking about black holes was Reverend Mitchell. He has already calculated that when you calculate the escape velocity from a certain body, you can actually come to a body, a dark star, which has an escape velocity of the speed of light, and nothing, I mean, if you then make this body larger, then nothing could escape from that body. The escape velocity from Earth, we know from the rockets that we are sending out into space, is 11.2 kilometers per second. The escape velocity of a black hole would be the speed of light, 300,000 kilometers per second. Now, the next point is light bending. Einstein has predicted in 1916 that the sun will actually bend the light from the stars behind it. And then Eddington, 1919, had made this wonderful experiment where he, for the first time, could show that indeed you can see in a solar eclipse, you can see stars which are actually behind the sun. So they are bending light in this way. And so you can imagine if you would squeeze down the sun by a factor of 2, then the bending of the light would be a factor of 2 larger. And if you squeeze it another factor of 2 and so on, you can just calculate how much do I have to squeeze the sun down until the light is bending back on itself. And this is basically the Schwarzschild radius that comes out from Einstein's equation. And so Schwarzschild radius, in principle, you can also say you can squeeze everybody fast, strong enough and make it or him a black hole. So if you, for instance, squeeze the Earth, squeeze the sun to a 3 kilometers radius, you get a black hole out. If you squeeze the Earth to a 1 centimeter radius, and if you squeeze your partner to the 10 to the minus 8 proton radii, you would also get a black hole out. And this brings us to this beautiful diagram that Maarten has already shown before. I like it as much as he. What we see here is the relation, the Schwarzschild radius for basically anything that you can think about, any matter in the universe from the smallest amount of matter up to the visible universe. And here you see the mass and the mass and the radius. This regime down here is the quantum regime, and the quantum regime is behaving somewhat awkwardly because it takes more and more energy to localize an object to a smaller and smaller radius. So if you would like to find smaller objects, you need a larger magnification, a larger looking glass, and you need more energy to confine it. And so the quantum region is going up here, the black hole region is going down there, and there is a very important point in this diagram called the Planck hole. Because when you are putting fundamental parameters in, you can actually define these Planck quantities. There's a Planck mass, there's a Planck radius, there's a Planck temperature. Everything, this is the smallest object that you can consider an object in physics. Because everything that you would like to make smaller, you would need more energy to put into a smaller piece. And then if you put in more energy, you automatically transfer to the black hole range. So at the Planck scale, physics is breaking down as we know it right now. And you can imagine physics of being more or less a kind of web, fluctuations consisting of black holes on the Planck scale. And this is where we believe that our universe has started. So if you, in very simple terms, you look at the history of our universe, it starts out at the Planck scale up here, then it goes through this little hiccup of inflation, but then in general it basically cools down. And the more it cools down, the more structures can freeze out, which were not able to survive before. In the same way as a lake is freezing and you create ice patches on it, the universe structures are freezing out. And it's actually a whole separate lecture about what we all know in this freeze-out process that I don't want to and cannot go into today. But I want to point out that the universe at the beginning was close to a black hole, and the universe today is still close to a black hole. Within give or take a factor of unity or so, or a factor of 10, the current visible mass in our horizon is close to a black hole. So you could, in principle, consider if the density of matter and energy in the universe would be larger than 1, suppose it would be 2 or 3 or 5, which we can rule out now, but suppose you think of a universe that has this larger space density, then from outside you would not be able to see any light from the universe, because basically from a distant observer the light would actually be bent back on the universe. And so you could imagine a universe which in itself is a black hole, which is another interesting concept. What we know about astronomy-wise is we know about stellar mass black holes that come out of the belly of massive stars. And we know about the supermassive black holes, which on this scale are actually very close together. Also, they are about a million or a billion times apart. So we are talking about 10 solar masses of the stellar mass black holes. We are talking about 1 million to a few billion solar masses for the galactic black holes. And that is what I would like to concentrate on in this lecture. So let's start out again from the pre-inflational space. So we have these fluctuations in space-time, and then instantaneously there is this inflation, and the fluctuations that have been there before are now frozen in and are producing the boundary conditions of our universe to start with. And then for some reason we have exactly the same diagram. You go through. It's just a beautiful diagram. So you go through the evolution that Maarten has explained to us. Now, Stephen Hawking did plot this diagram not just to visualize quantum fluctuations, but he plotted that in order to visualize what a black hole is actually doing if you are putting a black hole into this quantum gravity space-time. So here, this is a diagram where time is going in this direction, space is going in this direction. If you are putting a black hole inside of this space, then you basically have a dark region. And what he wanted to point out is that if you have a virtual particle which is coming close to the event horizon of that black hole, then it can happen that one partner of that particle is actually swallowed by the black hole. And then the other partner doesn't find his partner again, and so has nothing to do then to leave the system. And so basically from a distance, this black hole is spitting out particles. And this is the way the black hole is actually radiating energy. Now, it seems as if the black hole would create energy, but actually what you do, you have minus the energy of two particles here. When the virtual particle is created, one of those goes into the black hole, the other one leaves the system, and so the net effect is that there is one particle less in the system, and therefore the black hole actually has to pay for that. And on the long run, it has to pay in such a way that the black hole is actually evaporating, and the last whatever milliseconds of a black hole actually are expected to be a very rapid and ever increasing radiation and some kind of gamma ray flash or so. And the mere fact that we don't see these gamma ray flashes around us sets some important limit on the amount and the mass of the black holes that could be out there. So this is in simple terms how Stephen Hawking is explaining his Hawking radiation. And you can then also calculate what is the typical lifetime of a black hole. A lifetime depends on the size of the black hole. You can imagine that if you, for instance, would have virtual particles which are very close together, which have a very small wavelength, then it's very unlikely that one of them falls in. Then they both fall in. If you have particles which are huge, much larger than the event horizon of the black hole, then it's also unlikely that any one of those falls in. So it turns out that the Hawking radiation actually has the wavelengths of the size of the event horizon. So the Hawking radiation is basically something like a black body radiation with a peak at the size of the event horizon. And then you can calculate a black body is radiating according to standard laws of physics, and you can calculate how long it takes until the black hole has radiated away all its energy. And for stellar mass black holes, this is about 10 to the 60 years. And for black holes that are in the centers of galaxies and that are still continuing to grow throughout the future life of the universe, this is somewhere in the order of 10 to 100 years. So these are about the longest lifetimes in the universe that we can think of. Also, in Maarten's last but one view graph, there were several lifetimes which are even much, much longer. But I think just imagining that there are objects in our universe which we know, we can't grab them, but at least we believe that they are there, that have this huge lifetime, and thinking about the unknowns, the ignorance that we have about the future of our universe, what could happen to these objects is really mind-blowing. It's mind-boggling. Okay, now let's go back to more classical physics. We know very well how stars are forming and how they are evolving, and physics of stars is largely determined by the size, by the mass of the star. And so if you, for instance, have a star like our own sun, we know that it will actually grow as a function of time. We are right now in the middle of the sun's lifetime. Towards the end, it will develop, as we know, in about 6 billion years, it will develop into a red giant, blow off its envelope, and turn into a white dwarf. And just in passing, there was a nice joke that one of my teacher, actually, Kippenhahn, was always telling. He was giving a similar public lecture, and then a lady called him afterwards and said, "Oh, great lecture, but I was a bit worried, was this now 6 million or 6 billion years?" And then he said, 6 billion. Oh, God, thanks. Okay, the more massive stars are actually more shining brighter, and they give out their energy much more freely. And so a 10 solar mass star only lives about thousandths of the time, and the 30 solar mass star typically lives only a few million years before it explodes. And in both of these cases, so here you are producing a white dwarf. In this case, you are producing a neutron star that we have also heard in passing. And in this case, you are producing a black hole. So in principle, we know at least one process where nature can squeeze something fast enough and heavy enough that you can actually produce a black hole, produce so much pressure that you can squeeze the matter down to below the event horizon. And we have, in the last 15, 20 years, actually found fascinating examples of the creation of black holes, namely these gamma ray bursts that Maarten has also mentioned, where in the center of a star, a black hole is actually so powerful that it can pinch through the whole star and can basically destroy its own host star from inside. And we are seeing these gamma ray bursts and all the associated emission coming out of the star later. And indeed, when we are, the theme of this conference was actually the discovery of quasars in the 1962s with the very first cosmological redshift. And when you are looking at the development of how the frontier in redshift, the distance in the universe, has progressed, quasars were leading for a long time. Then they were competing with galaxies. But then, since about 1995 or so, the gamma ray bursts have been identified as cosmological sources. And so, as Maarten has said, the highest redshift gamma ray burst is now around redshift 9, and this is an amazing development. And so we see these gamma ray bursts to the very early universe, and so we know that black holes have been formed at very high redshifts when the universe was only about a 10th or maybe a 20th of its own life. And we also know that some of these quasars that I will talk about, the very massive objects which have millions and billions of solar masses, have not formed much later. So there is something going on in the early universe which is somehow favoring the formation of black holes. So now the big question is, how can you feed a black hole? I mean, we know that these objects, the gamma ray bursts, have maybe something like 10, 20, 30 solar masses black holes. We know that the quasars have about millions to billions of black holes, and the only way we can conceive is that during a very short time, this black hole must have eaten a tremendous amount of energy. And so the big question in physics and in astrophysics is still, how can you feed a black hole? I mean, how can you get this matter down to such a small radius in such a short time? Which, I mean, when you're thinking about black holes and you think, okay, that they are eating everything, they are pulling everything into themselves, it's actually not that easy. So for instance, if you look at the Saturn, the planet Saturn with its Saturn ring, the rings, I mean, there's nothing that eats those rings. I mean, the planet doesn't eat his rings as long as those stones in the Saturn ring are falling around the Saturn and they don't collide with each other, then there's no way that those stones can come down to Saturn. The same way with the planets. The planets are not falling into the sun because they are on stable orbits. And so in order to feed something and to bring matter down very closely to the central object, you actually have to have very special configurations, very special physics going on. And so feeding black holes is actually a big concern. And so let's look at the black hole in our own galactic center. We have some of the best information about the supermassive black hole in our own galactic center. When we are zooming into the galactic center, we are seeing these dark clouds. This is Sagittarius and Scorpius. We are zooming in. This is a movie that I've stolen from ESO. We are zooming into the very center, and with more and better technology, with adaptive optics and so on, we are actually able to zoom into the stars that are immediately surrounding our black hole. And it turns out that in the very vicinity of the galactic center, there is a star cluster which contains about 100 to a few hundred very young, massive stars. And these stars have actually been the matter of astronomers' attention since about 15 to almost 20 years. So since 20 years, technology has actually improved so that you could have infrared detectors. These infrared detectors can look through the dust and gas clouds. And there are two groups around the world who have specialized in looking at these stars around the galactic center. One of those groups is Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Garching, who has studied these stars for many, many years and has found that actually the stars are moving around the galactic center in very regular patterns, namely in ellipses. And the other group is Andrea Ghez here at UCLA, who used the Keck telescopes. And this is a picture where the Keck telescopes are actually finally pointing to the galactic center. So finally you know where the galactic center is. It's two laser pointers simultaneously. And you see that over many years, 15 years or so, you are actually able to follow the track of these stars, and there is something slingshotting these stars around with thousands of kilometers per second. So there is in particular one star that has moved around the center a few years ago with several thousand kilometers per second. So it's really fascinating to see this black hole swirling around stars. Now, the mass of the black hole can be easily calculated from these Keplerian orbits, and it turns out to be about 3.5, maybe 4 million solar masses. And so compared to other black holes that we will hear about, this is actually a relatively moderate supermassive black hole mass, but it is the closest example. Now, I told you that these stars, these about 100 stars that are swirling around the black hole, they are all young, massive stars, and we know that young and massive stars are actually radiating winds, so they blow out stellar winds similar to the sun, but much, much more efficient. And so the question is, I mean, even if the stars themselves don't fall into the black hole, why doesn't the wind from the star, or why is not there some matter that is actually accreting onto the black hole? Because the black hole itself is basically has been invisible. In the meantime, as I will show you, it has become visible every once in a while. But let me first show you this beautiful NOVA movie that has actually been done in a collaboration with Andrea Ghez and Reinhard Genzel, where you actually zoom into the galactic center. The galactic center is full of gas and dust lanes. There's all kinds of complicated structures of previous encounters of matter that has probably fallen into the galactic center. And then we are coming close to the stars, which are swirling around the black hole, and you see that In the meantime, we have about 20 or 30 orbits of individual stars. If you throw the data of Andrea Ghez and Reinhard Genzel together, there are about 20 orbits known. And the black hole itself is almost invisible. And the big question is why is this black hole so quiet where there should be enough matter around that the black hole should actually happily accrete and eat. And so there is actually one simulation that has been done in Rashid Sunyaev's group at the Max Planck Institute for Astrophysics, where they were taking the real position of these stars, of the stars close to the galactic center, and then they gave each of these stars a stellar wind blowing out, and then they were calculating what happens to this wind. And that's actually interesting. The black hole is somewhere in between here, and what you see quickly is that the matter of these winds is actually then swirling around the black hole and is producing a little disk around the black hole. But the disk has a hole in the center. And so this is exactly, similar to the Saturn rings, basically. There is matter. It's swirling around its central star, but the matter is not dense enough and is not, doesn't have enough viscosity, so to speak, to actually provide enough friction that you can get rid of the angular momentum and you can get down to the black hole. So this is the main reason why our own galactic center black hole is so quiet. There is a lot of matter around, but it just doesn't get down. So it's actually not easy to feed a black hole. Nevertheless, we now know that every once in a while, actually about once a day, our black hole is taking a little snack. It's eating about the size of a mountain or a small comet. These are almost simultaneous XMM Newton and VLT observations. XMM Newton has found a huge flare in the galactic center where the radiation all of a sudden increased by a factor of almost 100. And in the infrared, you actually see even more details. You see flares, and you see actually substructure in these flares. So if you calculate the amount of matter that is eaten there, it is, as I said, roughly Mount Everest or a reasonable sized comet. And so there is some matter around. We still don't know whether it's just gas clouds or there are some models where it could actually be asteroids or other things that are coming together with these stars. So the Kuiper belts of these stars or other things that can actually every once in a while be accreted on this black hole. And there's a lot of information that you can get from observing simultaneously. Actually, this picture that we saw where Andrea Ghez was observing with two Keck telescopes the galactic center at the same time was exactly to study these flares, because she was observing with different instruments simultaneously to get the spectral shape and to learn the physics about how these accretion processes happen. So there is a way to feed black holes, but this is a very feeble way. It would take basically more Hubble times to grow a black hole to a million solar masses with just comets and Mount Everest. So that's too little. However, more food seems to be on its way. So actually the black hole is no longer expected to starve forever. There is actually a very interesting discovery, but also a very interesting debate in the community currently going on. Stefan Gillessen has found an object which is not a star, or at least doesn't look like a star. They explain it as a gas cloud, which is actually on its way to the black hole. So they only have recognized this recently, that one of these objects, which they originally thought is a star, is actually on a different trajectory and could well be a gas cloud of a few hundred or 1,000 solar masses or something like that, that is on its way to the black hole. And simulations of this gas cloud show that in principle here is the clock ticking up, 2005, 6, 7, 8, 9. So roughly now, roughly in summer 2013 until roughly summer 2014, this gas cloud should actually come so close to the black hole that it is partly disrupted by tidal forces, and then some fraction of the gas cloud should actually accrete onto the hole, and the black hole should get happily brighter. And so this is a bright future for our own galactic black hole. Don't be worried, it doesn't outshine the galaxy, so it's still a relatively small amount of matter. However, there are debates. Actually, Andrea Ghez does not believe that this is a gas cloud. What she believes is that this is a star which is actually bloated up very large. So a super Wolf-Rayet star or something like that. So the difference is that this star would also pass close to the galactic center. It would probably also leave a little bit of matter behind, but the gravity of the star is big enough that it would keep its matter, and so it would not produce fireworks in the next few months. So watch that space. It will stay interesting to see what develops with this black hole. But this brings me to the topic that, in principle, black holes like these are able to eat whole stars. If some of these stars which are swirling around the black hole is coming close to the black hole, and this has actually been predicted by Maarten in 1988 already, if a star is coming close enough to the black hole, it can be disrupted by the tidal forces of the black hole, and then some fraction of the black hole, of the star, are actually eaten by the black hole. So like in this case, there is one of these little poor stars, which on one orbit comes too close to the black hole, and then it's basically its end. Its face is sealed. Its face is sealed, and actually the black hole is not a very good eater. It only takes a fraction of the star. The rest is blown away into the interstellar medium. But that amount of matter should be enough to actually let the black hole shine for several years happily and become very bright. And actually, I think more than 10 years ago, we believe that we have seen events that could be interpreted in this direction. There was at least in particular one event which we discovered with ROSAT, which increased basically to 10 to the 38 to very bright luminosity, and then decayed on a timescale of about 10 years, according to the predictions that it should have done. And this is actually, in the ROSAT All-Sky survey, we have found 4 of these objects over half a year, and that would in principle be consistent with the predictions that this should happen in a galaxy every 100,000, roughly 100,000 years. So in our own galaxy, it should not happen very soon, but if you are looking at many different galaxies, then you can see these events almost every day in principle. And indeed, similar events have now been detected by the SWIFT satellite, which is actually more believable even because it's hard X-rays at very high luminosities. And another object has been found by a combination of GALEX, of the GALEX satellite, and Pan-STARRS. You know that GALEX was built here at Caltech. This event is actually, so before I go to the GALEX Pan-STARRS event, I'm first referring to the 2 SWIFT events. SWIFT has discovered many of the gamma ray bursts, which have a duration of around 1 second to about 100 seconds. And then it also has discovered some events which are extremely long for several hours, which are associated with very massive Wolf-Rayet stars. But it has also detected some events which take months, and they are interpreted as these tidal disruption by supermassive black holes. Pan-STARRS is a survey telescope at Haleakala. We are actually, this telescope is working since 3.5 years. We are now building the second one. It already had first light a few weeks ago. And Pan-STARRS is making a movie of the sky. It basically covers the sky several times, and it's in particular sensitive to things that are moving, like, for instance, killer asteroids and comets, but also to things that are flaring up, like supernova explosions. And Pan-STARRS, together with GALEX, has found one object where we believe that this is a Nature paper from last year. We believe that the event is still going on. This is a simulation of one of the more detailed simulation of one of these tidal capture events, and it has been discovered late 2011. And ultraviolet observations with GALEX and then further spectroscopy and so on showed that this event is basically still going on while we are speaking. So it's very interesting as well. So I think we have the glimpse of these so-called tidal capture events. But now when you calculate one star every 100,000 years, this is still not enough to really feed a black hole to a really sizable to a supermassive black hole. So again, this is very interesting, but what we really need are black holes that are eating one star a year roughly, or maybe even more. So how do you get a star every year down to this very small region of the black hole? And this is where actually we will come back to later. This is where the merging of galaxies is actually playing a very important role. Before I do this, I would like to now invite you to a journey through our local universe. You know, at the end of Maarten Schmidt's talk, you have seen this beautiful Virgo simulation where we were flying through a simulated universe. Now I can show you the real thing and fly you through our real universe with real pictures. And this is a simulation which is also one of these cosmological simulations. But the special thing about it, it has been done in Potsdam and others in my previous institute. The special thing about it is that this has been simulated so close, I mean, as close as possible to our real environment. So there is the Coma cluster, there is the local supercluster, the great attractor, the Perseus Pisces region. And when you zoom into here, I mean, we are here roughly. When you zoom into, then you have the Virgo cluster, and you have the local group, and this is our galaxy, and this is the Virgo cluster. And so what I now can show you is actually a film where we are traveling from our local group, from our own galaxy, to the Virgo cluster. That movie has been made by Brent Tully at IFA, and it's actually made up of real images of the galaxies, which are also in real three-dimensional space, because Brent Tully has developed a method where you can determine the distance to the galaxy. So you can really get a full three-dimensional grid of our local universe. So let's go, and now I have to switch on the sound here, because this is now coming with sound, and I have to keep quiet. So you probably know this constellation. This is Orion. And now we are flying from our own galaxy, from our own Earth, our own solar system, into the nearby universe. I've always wondered why Strauss knew how fast this travel would go to the Virgo cluster. So we are in the center of the Virgo cluster, and we have this fascinating object, M87, which is actually the most closest massive black hole to our vicinity. It is about a galaxy that is about 1,000 times bigger than our own Milky Way. And indeed, the black hole in the center is also about 1,000 times bigger than the black hole in the center of our own Milky Way. We will come back to the fact later that we now believe that every galaxy has a black hole, and there's a very strong relation between the mass of the galaxy and the mass of the black hole. But let's first zoom into these fascinating events that are happening here. And this is very reminiscent to the 3C273 case that Maarten has discovered 50 years ago, where why we are celebrating this conference here. So when you are looking at that object in the radio, it has fantastic jet-like structures coming out and hot electrons that are producing synchrotron radiation. When you look at it with the Hubble Space Telescope, you see this jet it's coming out like a machine gun fire. And in the X-rays and in the radio, you see that is embedded into hot gas in the Virgo cluster. And so these so-called active galaxies that Maarten also showed one case in the center of the Perseus cluster have a very strong effect on their environment, and the feedback from these galaxies is actually an important element. Now, I have another movie which is not a simulation and not a real picture. It is actually a more Hollywood-type movie, but motivated by real physics. I can show you a movie that is made by an astronomer with the name of Stefan in Mexico, who has actually motivated how the accretion process in the center of such a black hole might happen, and how in particular these fantastic jets that are coming out, like that are seen in the Chandra Observatory, in the X-rays, in the Hubble Space Telescope, at the VLA, how they could actually happen. And so this comes with music as well, so I have to keep quiet, sorry. The center of the galaxy was surrounded by almost like a pizza-like disk, a very thin disk, which is getting very hot in the center. In the center, the matter swirling around the black hole is heated up because of the amount of friction which is in the disk. The matter is heated up to temperatures of several 100,000 degrees, and in the very center, relativistic effects happen where hard X-ray and gamma-ray radiation are produced. And then every once in a while, the black hole is actually not able to swallow all of the amount of matter. The disk is getting unstable, and there is not just a belief, but there are physical evidences in nearby black holes that this relation, that the disk is then collapsing, and then as a consequence of that, these jets are spit out, is actually motivated by observations of Sept galaxies and microquasars. We still don't know exactly how these jets are working. Also, Roger Blanford gave a wonderful talk today, which is motivating everybody. But it's clear that magnetic fields are playing a strong role, and so these jets are somehow a very complicated physics connection. What I wanted to emphasize is that in this disk, we have also seen stars swirling around. And the stars that were actually then processed through the disk is about 1 to 10 stars a year. So this is the real happily eating black hole and getting fat. This is the phase in which the black hole is really getting very, very fat. And so this brings me to what I said. One of the few, I think, cases that we can think of, one of the few interpretations how you can actually make such a black hole eat so much is if you have mergers of galaxies and then also mergers of black holes. And so the idea behind that is that if you have two galaxies, every once in a while it happens that they are coming so close to each other that they are actually gravitationally bound to each other, and then they start to merge. And if it is true that there is a black hole in each of these galaxies, then it's clear that at some point these black holes should also come so close to each other. And indeed, this was something that we have done. Oh, yes. Sorry. That we have done when I was still in Garching with Stefanie Comossa. We have looked at one of these train wrecks that Maarten has also shown, merging galaxies. And in the center of this train wreck, this is actually an optical image from a 2.2 meter telescope, but now it's much nicer in a Spitzer Hubble Space Telescope picture. There are two nuclei which are believed to be the remnants of the two previous galaxies. And we have looked at that center of the galaxy with Chandra, with Stephanie Comossa, and in the meantime there is a much nicer picture, much longer observation by Claude Canizares at MIT. There are clearly two hard X-ray sources, and if you look at their spectra, they have all the characteristics of a black hole, which is happily accreting. You don't see them in the optical because they are completely smirked by gas and dust, but we can calculate from the X-ray properties that they must be happily shining, I mean, similar to quasars, but they are so-called obscured quasars. And so what we believe to see is, from this simulation that you have already seen from Maarten, at the phase of the train wreck, which is roughly now, we are now zooming into the center of the galaxy, and there are these two black holes which are still swirling around. And now it's a matter of probably 100 million years or so from now that these black holes are coming so close to each other that they are actually then merging with each other, and then they are shaking the space-time, producing gravitational waves, which we hope at some point to be able to measure with LISA, with the Gravitational Wave Observatory. But don't worry, I mean, these waves are minute. They are only 10 to the minus 25 or something like that of a meter, so they don't shake us very much. But with the beautiful gravitational wave observatories, we are hopeful that maybe in the next 10, 15, 20 years we will be able to see the gravitational waves. So it was realized, I think this observation triggered a whole train of thought. What was not known before is that actually already before the black holes are merging, they can actually have a very large luminosity, very high power. And that was then, I think, roughly at the time when people realized that the cosmological simulations required significant feedback from these black holes into the galaxy. When you have such a large amount of radiation process, then actually the binding energy of two of these black holes is much larger than the binding energy of the gas in the galaxy. And so if you just find a way to turn that binding energy into kinetic momentum, you can actually get rid of the gas. And this is something which has triggered a whole industry. And we got a beautiful talk by Phil Hopkins yesterday. He also showed these simulations by Volker Springel and others, where you are now having much more detailed simulations of galaxies when they are merging. And here the interesting thing is that the stars and the gas are separated out separately. So you can look at how this interaction happens, this train wreck is developing, how the gravitational forces are producing these long tidal tails, both of the stars and the gas. And the disk-like configuration is then ultimately completely reconfigured into a spherical, or round configuration. And so the merger of two of these disk galaxies in the end ends up as an elliptical galaxy, a round elliptical galaxy. But what was not known before, and what is now, I think, a kind of standard conundrum, is that the energy that comes out of the black holes is enough to blow away all the gas in the galaxy. And so you are ending up in the end with a dead and red elliptical galaxy. Actually the feedback of that black hole onto its galactic environment has a very strong role in shaping what the galaxies are looking like. Basically, the black hole is shutting off the star formation. It doesn't allow any new stars to be formed, and therefore the black holes have actually a fundamental role in how galaxies are looking like that today. And as I already said, the binding energy is enough to get rid of all that gas, and I think the physical simulations now and what we have seen at this conference as well shows that it is indeed possible to get this binding energy out into the intergalactic medium, or in the interstellar medium first. So this is actually then also invoked this process to explain possibly how the very early quasars have formed. This is a simulation which is trying to explain how you can produce a quasar with 10 to the 9 or a few times 10 to the 9 solar masses when the universe was only about 15-20% of its current age. And the trick that they have found, the trick that maybe nature is applying, is that you have continuous merging. The problem is that this merging is happening very fast, and so it's only an episode in the life of a galaxy. It is in principle not really long enough to feed the black hole to the very fat mode. But if you have several small galaxies which are merging with each other, then you can actually sustain this accretion mode over almost a billion years, and then you can grow something of the order of maybe a few thousand, 100,000 solar masses into something of the order of several billion solar masses. And this is happening only over a very short time scale in the universe. And we believe that what I told you before, this is the relation between the mass of the black hole in a galaxy and then, in this case, the speed with which the stars are swirling around the central galaxy. And there's a very tight relation. Big galaxies have big black holes, small galaxies have small black holes. And this tight relation is interpreted as a consequence of this feedback mode. Basically, it's like a thermostat. When the galaxy is getting too hot, the black hole is shutting off the heat and is basically then not allowing the galaxy to grow any further. And so this fundamental relation between galaxy formation and black hole evolution has now actually led to the fact that these two fields, galaxy evolution and black holes, are very tightly integrated, and that has actually caused a much larger audience in astrophysics to believe that black holes are important. So, I already showed you the first proto-quasars. The things are getting more and more challenging. The highest redshift quasar that we have seen in Maarten's talk as well, at redshift 7.1, has about a few times 10 to the 9 solar masses, and these simulations are barely able to really make it up to that moment. And it is believed that you have to start out with something which is already quite sizable, and it is still completely unclear how these seeds of the supermassive black holes are formed in the first place, whether they are formed from individual stars, like a gamma ray burst, or of something more exotic, so-called quasi-star or superstar. If I still have time, I can come to that towards the end. So now I just give you a short glimpse of my own work in this field, which is trying to understand how the black holes are actually not just formed, but how they evolve, how they grow. And this is not just my own work. There are many people in the audience, McGurry and other groups are working since many years about that, because it's the combination of X-ray observations with optical and infrared observations, and a significant part of this conference was actually dedicated to this topic. It starts out with the X-ray background. The sky is full of a glow of X-rays that was discovered basically serendipitously in a rocket flight by Riccardo Giacconi in 1962. And then with the Rosat satellite, which made this beautiful picture of the moon, and then also a beautiful picture of the whole sky, where we see this X-ray radiation distributed over the whole sky, we were able to resolve this cosmological signal into many individual objects. And it turned then out, and this is the work that we did originally with Maarten Schmidt. Maarten Schmidt had the access to the big telescopes Palomar and Keck, and we were able to identify these objects with quasars, basically, at the early time in the universe. So the X-ray background then was later studied with Chandra and XMM Newton. The X-ray background turned out to be the integrated signal of all black holes that have ever basically grown in the universe, and it's a kind of archaeological record of how the black holes have actually grown and developed as a function of time. And one of the fields that is actually very important in this realm, and that is also thanks to Nick Scoville here at Caltech, is also a Caltech product, the Cosmos field. The Cosmos survey is now, I think, the part of the sky that has been studied extremely well. It's about a 2 square degree field, 10 times or 30 times bigger than the moon. This is a Subaru and Hubble picture of the Cosmos survey, and I was responsible for doing the X-ray observations. And when you are looking at an arbitrary patch of the sky, then you are seeing, in this case, about 2,000 black holes. And the different colors of these black holes, all these little dots, tell us about how much matter is around them, how much obscuration is there. and also how far they are away from us. Because if you have a very blue object, this means that it is only observed in the very hard X-rays. It cannot be too far away, because otherwise it would be shifted in the red. And so to study the cosmological evolution of these black holes, it takes a large amount of observing time on optical telescopes. And many of the people in this room are actually working on similar topics on the cosmos field, on other deep fields to get the signals out. In passing, I would like to mention that the clusters of galaxies that Maarten referred to, the hot gas in the clusters, which are a very strong constraint on how much total matter is there in the universe, 0.3, omega equals 0.3, comes from these diffuse patches around galaxies, so this is the second most abundant source of X-rays, clusters of galaxies. Okay, what we have done over the years, and when I mean we, many different groups in the world have contributed to this field. And in the meantime, this has been done not just in the X-rays, but also in the infrared, in the radio and everything. What we have found is that the most luminous, the most massive quasars are actually where they have already been placed by Maarten Schmidt and others at high redshift, when the universe was only about a quarter or so, or 15% of its age. This is what I would say the puberty of the universe, the puberty phase where the universe was very active and very massive objects have been formed there. Interestingly enough, there are many, many orders of magnitude more density of lower luminosity objects, which are much less, so to speak, radiating, and they are coming much closer to our home. They have been radiating for a much longer time than the early quasars. And this so-called downsizing effect, the anti-hierarchical evolution, that things are actually not growing with time but are getting smaller with time, seems to be a fundamental property of how the evolution in galaxies is happening. And I just wanted to come back to this diagram. So I have turned it around now, so unfortunately this you cannot read the letters anymore. But the quasars basically happened at a time after the first galaxies have formed, when when the galaxies were the universe was still much smaller than today, but the galaxies were already alive. And so it was actually much more often happening that two galaxies are coming close to each other and they are merging with each other. In the meantime, the universe gets larger and there are fewer and fewer galaxies to merge, and therefore this peak is going down. This is my interpretation of this phenomenon. And what we are seeing in this X-ray background is actually coming much later, much closer to home. And this must be effects that are happening in normal galaxies like our own, where we are seeing accretion processes, I mean, not just single mountains and comets or stars, but every once in a while, even a galaxy like our own is undergoing an accretion process, and that happens in about 10%, or maybe, as we have heard from Louis Ho at this conference, about 30% of all galaxies have some sign of accretion, so it seems to be a quite normal process that the black hole every once in a while is getting something to eat. Now, in the last minutes, I would like to concentrate on very recent work where we are now trying to get information about this very early phase where, that is called dark ages in Maarten Ries's lecture, where we hope to get somehow a fingerprint of the very first stars. The objects are so far away and they are so faint that we cannot yet see them individually with our telescopes, but we can still infer that they must be there. This is similar to, for instance, sometimes you have lightning at the very, very far in the horizon. You don't see the lightning anymore, but you still see the glowing of the lightning. Or if you see a fireworks from a distance, you don't see the individual explosions anymore, but you still see the distant glow. And this is something which we are trying to do both in the infrared and in the X-rays. But before I come there, I want to reiterate. So the modern view of evolution of galaxies is we believe that they are merging, that they are producing binary black holes. The black holes are merging, are producing these powerful quasars, which are the topic of our meeting. These powerful quasars are then producing elliptical galaxies. They are blowing out the gas of their galaxy. And then, if you wait long enough, then maybe such an elliptical galaxy can turn into a spiral galaxy again. Like our own galaxy, for instance, has an elliptical galaxy in the center and a spiral galaxy outside. So if you have long enough time, then some of these elliptical galaxies can turn into spiral galaxies. And then in principle, for instance, our own galaxy goes through the same cycle as Maarten has told us in 4 billion years, and it will turn into a quasar very likely. So now let me come to the very last parts of the X-ray background. So we have in the meantime resolved about 90% of the X-ray background with XMM, Newton, Chandra, and Rosat. And the objects that we are seeing are roughly out to redshifts, mainly out to redshifts of 3. And then what we can also do is we can use all the Hubble Space Telescope observations, all the deep imaging in the cosmos field and elsewhere, in order to find the average X-ray emission of the sources at a redshift 3 to 5. But then there is still something left, roughly 1% or so of the emission. And this emission might very well be from redshifts beyond 7 to 10 from the first population of sources. And so how is that, how can you imagine that that happens? So here is the last scattering surface of the microwave background. Then there are these cosmic dark ages, and then there are the very first objects that are forming, very likely the first stars. And then potentially some of these first stars will also turn into black holes. And so what we have done in a group led by Sasha Kaszlinski and in the X-rays, Nico Capiluti, my former grad student and postdoc, is that we have correlated the diffuse signal. I mean, you basically take the signal of Chandra and Spitzer, and you take out all the objects that you know and that you can detect individually, so that you have only background left, only diffuse emission. And then when you correlate these two, you find that you actually, there is a strong signal where you have fluctuations in the infrared background, and you have similar fluctuations in the X-ray background. And that means that there must be some population of sources which are too faint to be resolved individually, and they could very well be from the very high redshifts, from redshift 7 to 10. This is a field which is still in development, so watch the space. I think in the next 10 years or so we might see much more of those, and maybe we are able with JWST and with ALMA and other telescopes to maybe even resolve some of these early signals. Ideally, I agree with Maarten, we need a new X-ray observatory which is more powerful than Chandra, where we can then also see these X-ray objects individually. But this is probably beyond my own horizon. Now let me come to the last picture, which is more or less a graphical representation of what Maarten has given us in his last but one view graph. So this is the long future of the universe. So what is here is the current age of the universe is about 10 to the 10 years. It's actually 1.3 or so, 1.4 times 10 to the 10 years, but let's give it 10 to the 10. Then when you go to 10 to the 20, it means that this is 10 billion times more than 10 to the 10. So it's already unimaginable. And by that time, the stars will have burned out. All the gas in the galaxies and so on will actually have been processed into new generations of stars. And what is left is more or less the graveyard of the stellar evolution, namely white dwarfs, black holes, neutron stars, all these objects that are living much longer than stars. At some point, we don't know when exactly the white dwarfs will actually be able to annihilate dark matter, depending on what dark matter actually is. But there is a model which says that if the dark matter is consisting of particles and antiparticles, that these particles and antiparticles will actually every once in a while come by the center of a white dwarf, and then they come so close together that they can actually annihilate with each other. So this would be the ultimate, more or less, fate of these original quantum fluctuations that have pulled out the particles from the vacuum in the first place. And then if you force them close together, then they can find their partner and annihilate again. Then at some point, physics says that protons will decay. Also, again, we don't know exactly. I think when I started to study, that was about 10 to the 30, but in the meantime, the upper limits is actually going up and up. So we have not yet seen a single proton decay so far. So it's also part of this exclamation mark where physics is getting uncertain. But then it's actually fascinating that in the end, when the protons are gone, when the dark matter will annihilate, we will still be left with black holes. We will also be left with some white dwarfs, some neutron stars. But the black holes, I want to zoom into them. Because what I wanted to say is I have, on our travel to the Virgo cluster, we have visited the black hole in M87. M87 was probably the very first object in our universe, when you think about it, in our local universe. It is the center of the largest mass concentration in the Virgo cluster in our immediate vicinity. And so it was very likely the first object that was formed. And so the black hole in the Virgo cluster is very likely the oldest single object that we know in our local environment. It is also one of the most massive objects, and therefore it will last longest. So one of the first objects that has entered the stage of the universe will also be one of the last to basically leave it. It's still unclear in the fate of the universe whether we will ever be merging with the Virgo cluster and whether we will actually ourselves fall into the black hole of the Virgo cluster at some point. Because I think the predictions about the motions of galaxies and so on in the local universe are still not completely clear whether we are bound to the Virgo cluster or not. Also, I think I'm not a specialist in this field. But it's just fascinating to see that objects that we know today and that we are studying and love will be the last objects to leave the stage of the universe. And then in the end, the universe basically started from nothingness. It will end with a nothingness. But in the meantime, many other universes may already have been created. And so thank you very much for your attention.